Alright everyone, thank you guys so much for coming out here today, and thank you Dragos for inviting me to speak. I really love doing this. I just love neural networks. It's like they're my favorite thing, I guess you could say, in the entire computer program world. So I'm really stoked to come and speak to you guys. So a little bit about me. I'm actually I'm gonna slide this just so I can actually see my own what the heck is on the screen without having to look all awkward and backwards. So I've been a neural network enthusiast for most of my life. Actually, when I first got into it, artificial neural networks were kind of a joke, and they really weren't very popular. They were something that you read about in a book, and I never really had the chance to apply them in any sort of real application. But until I got to a company called Sensible. And by the time that I had gotten there, I'd always been a believer in neural networks, but I'd never actually gotten to actually try them out. And then at Sensible, we developed receipt processing technology, where we take images of receipts and we turn them into JSON objects with all of the structured data, and then that can go into a subsequent system which gets analyzed and further processed. And more recently, I left Sensible to start doing my own deep learning platform, just because I loved it that much. And so that's sort of where I come from. So I'll start, why are neural networks shunned by the data science community? And I get this a lot as I'm going out and I'm preaching these things. I'll often get a lot of pushback from data scientists who will say, oh, that's overkill, or that's too much, or why would you bother using neural networks when you can use a simpler model or a more efficient model? They were invented in the 1970s, and the basic fact is that they use way too much CPU power versus the benefits. You would have to, they take a long time to train, whereas with models like linear regression, you can get the result in 1 or 2 passes. Whereas a neural network, you have to do hundreds of passes over your data set in order to get them to work. So they're really very, very inefficient. So people didn't really want to use them. So what changed? Why are neural networks now getting more popular? Why is deep learning sort of replacing these other techniques? Actually, before this point is that neural networks are capable of approximating all other techniques and the results of other techniques. So the effect of things like Moore's law and the continuing increasing of CPU power meant that the fact that they're inefficient mattered less and less over time. We had better optimization techniques. Everyone talks about stochastic gradient. I have not actually trained a neural network with a vanilla stochastic gradient algorithm in a long time. Now we have really good techniques like Atomax and Attergrad that can work very reliably across a whole bunch of data sets without having to do much tuning of the hyperparameters. Then, of course, I think one of the big one, of course, was inventing the 2 types of neural networks that are really dominant today, the LSTM, which behaves like memory and remembering things, and the convolutional network, which behaves as a pattern matcher. And so these sort of like simplifying architectures really, I think, push the whole field forward. And so now why am I still getting this pushback, actually? I mean, deep learning was really popularized, or started to get popular around 2011, when people invented the first library that could train a neural network on a GPU, and it's been up and up and up ever since then. But yet, there's a lot of industry momentum behind classic data science techniques. K-means, manual feature selection, these big data platforms that a lot of us may be forced to work with, they were designed in the previous era. And just so while the industry results and the academics have shown that neural networks can work across a whole wide variety of problems, the current techniques still work well, and they're the ones that are implemented in whatever big data platform that you might be forced to use because of your workplace. And the other big reason that I think there's still a lot of pushback is that you have to accept the black box. There are ways to dig into why a neural network is doing what it's doing, but you're actually just better off not even bothering and going down that road. It's extremely time consuming. to try and figure out what's happening at each layer and what those different parameters are. You're better off just accepting the fact that it just does what it does and it gives you the accuracy it does, and instead focusing on like an ends justify the means way of looking at it. So I would say the fundamental advantage of adopting deep learning and neural networks versus using classical techniques, first, you only have to learn one technique, or you really, the main thing that you have to learn when working with neural networks is how to experiment. Do I go with 5 layers or 6 layers? Am I going to use a ReLU or a TANH unit? Am I going to use, am I going to put regularizers at every layer? I'm going to put one regularizer somewhere in the middle. All you have to do is really learn to play around, whereas I think with classic things, you really had to fit your choice of model to the problem and what type of problem. The other big thing, it processes data raw, and this is actually mostly what I'm going to be talking about today. This is a huge advantage of neural networks, that you don't have to go in there and manually prepare features and analyze your data and apply domain knowledge. That you can just, in many cases, just shove the data in and let it work. And of course, now that you don't need that domain expertise, you don't need to hire a fintech data scientist, because really that domain expertise is no longer relevant. It now makes hiring cheaper, because you could hire anyone who's got that familiarity with the experimental process, rather than needing to work with someone who's specifically experimented with deep learning. So I'm going to jump in more specifically on how deep learning could save you guys as data. Actually, maybe I should ask, how many of you guys are data scientists, like practicing data scientists? So I guess the rest of you are just here to learn and find out something new. Well, wonderful, wonderful. So for the few of you who are data scientists, I'm going to try and explain why it saves you time, and why it saves you time versus using a decision tree, versus using XGBoost, versus using all of these classic techniques that you might be used. So the basic, I'm going to walk through a bunch of examples actually. So the first example, cross-correlated variables. If you're a data scientist, you have 2 variables that you're trying to feed into a model, and they are highly correlated with each other. This is a big problem. In classic techniques like PCA and k-means, having 2 variables that are very similar would mean that they double the effect on the final result of the clustering that you're going to do, or on the final result of the PCA algorithm. With a neural network, there's really no such restriction. If you have cross-correlated variables, due to the stochastic nature of the neural network, it's just going to instantly pull them together as being one common parameter. So the neural networks don't have that same implicit assumption behind them that you don't need to remove your cross-correlated variables. So one of the big steps, if you do a lot of data science, first check for those cross correlations. You don't need to bother doing that anymore. Just put the data in and find out. So the next kind of more interesting one, say if you have missing values. Say you have data where you have a column and only half the time the value is there. In traditional ways of doing data science, this is a big problem. You can't train a decision tree when half the time the value is null. That's not really, doesn't teach the model anything that's significant. Whereas with neural networks, you don't need to just do something like skipping the row, or actually what we often do is actually build a model just to impute that value, to guess what that missing value is, so that it no longer affects, the fact that it's missing no longer affects our results. This is really very slow and very painful to do, to build submodels just so that your data is clean enough to feed into your final model. So with neural networks, we can just feed zeros. It may actually sound crazy to you, but you can, for these cases where you have no value, feed no value into the neural network, which would just be a vector of zeros. And the neural network, so long as you have sufficient data, can learn around this fact. And as a result, still learn the pattern from the remaining variables, and you don't need to do that cleaning anymore. And I'm going to keep going. So with processing text, for example, in classic methods of processing text, you have to build up a model which essentially destroys the order of the text, where you might, for example, try to figure out which word is the most important word in the text, or that would be TF, IDF, or you might just say, okay, I'm going to build something where I take, if the word exists or not, it's 1, if it doesn't exist, it's 0. This would be a bag of words model. There's really, you lose a lot of information doing this. So my suggestion is, again, with neural networks, you don't need to destroy the order. You don't need to do all of this hand preparation and hand coding of your data. You can simply use a recurrent neural network and feed that neural network into a larger part of the model. Further, in more generally variable length data, this actually came up for me recently with fraud detection. So the most common technique still with fraud detection is to manually construct a decision tree. What they actually do, and I almost got this deal to work on this piece of software, they all have interfaces where you have specialists in fraud detection going in and saying, okay, well, I'll prune this part of the decision tree and I'll add this if variable in. It's not even machine learning at that point. What they're really doing is they're manually constructing these techniques. And so with fraud detection, for example, you will have a whole bunch of hand-prepared features like what purchases I made, what is my most frequent purchase restaurant, or my last purchase location, or you'll have like hundreds of them. How much I purchased at Walmart, or how much I purchased at McDonald's, or how much I purchased at my most recent restaurant. All of these variables that you would feed into that model, and this really destroys a lot of the inherent information in that sequence of purchases. So what we can do, again, with a neural network, you don't have to flatten that data and hand prepare those features. You can just directly feed each transaction one after another. Best Buy $50, Future Shop $70, McDonald's $6. You can't get any McDonald's for $6 anymore, but there's so on and so forth, right into a recurrent neural network. So the power is that we have so much flexibility with the construction and design of recurrent neural networks that you don't need to think about the model. You just need to think, what is the structure of my data, and that implies the design of the model. This one, I always love talking about this. So with small data sets, one of the big issues that we have dealing in classic models is working with small data sets. And the main issue there is that in the way of doing this with classic data science is that you're just going to make up for the fact that you have not that much data by hand preparing features with your domain knowledge of the situation. So you're just going to say, okay, well, I understand that the data works in this way or that way, and I'm going to massage this data to kind of get the result that I'm expecting. Now, with neural networks, there's an extreme amount of flexibility to essentially take a larger semi-related data set and transfer the learning from that larger data set into your small model. The classic example here is text. So what we do is we train models like Word2Vec, and Word2Vec essentially takes a very large amount of text and finds the context for each word. In a way, it's finding the meaning of the words. And they've actually found very interesting patterns when you train Word2Vec models, like with words king and queen, they'll be linearly related to the words woman and man. So you find inherently that it's with these word vectors, you're not just getting a random vector describing, you're encoding the meaning, in fact, the high-level concept of a word. So we take a learning that's basically applied on every website across the internet, and the Word2Vec model that I use most frequently is trained on, I think, like every book written before 1980, plus all of Wikipedia, plus some other data set called GigaWord, and so the amount of data there is enormous. It's 100 billion. But then I take that knowledge, that Word2Vec model, and I'm applying it to a data set with my client, which might be only 1,400 rows large. And ordinarily it would be very, very difficult to work with such a tiny data set. But because we have that understanding of the meaning of the words taken from a larger data set, we can actually operate really well in this data set. In another case, we can talk about image classification, where this is really shown to be very effective. What we'll do is we'll train a model on ImageNet, which is, I think they're up to like 14 million images now. It's an enormous, enormous database of images that have been categorized into like 1 out of 1,000 categories. I think actually they have way more categories, but they have standard versions which are 1 out of n categories. So you'll train a neural network on that enormous ImageNet database to take an image and tell you what's in it. And then you chop off part of the neural network. That basically you chop off the top part of the neural network, you just ignore it. And then you take the remaining part of the neural network and you give a new top part and you train it on your small database of images, like a database of cars. And this can massively improve the accuracy of your results. And it may seem silly that training a neural network to classify on this one data set would improve the results on classifying on this other data set. But when you have really small data sets, this actually is just shown in practice to work amazingly. And a lot of what we found with neural networks is empirical results. No one really totally understands why it works that way. It's just that we know that it does because we've found it out empirically, and we've tested it and we've seen, okay, this is better than training a model directly. So transfer learning, I think, is like a huge opportunity that's, it's very difficult outside of decision trees, and not even random forest, really just plain decision trees to actually do any transfer learning. So again, even more, so clustering. When you have, k-means clustering is actually extremely, extremely, painful. If you've ever tried to do it, it is very, very sensitive to what features you chose to include in your model. Again, like the cross-correlated variables. If you have two variables that are very similar, they're going to have twice the impact on your cluster than you otherwise would. Whereas with neural networks, what we can do is we can take a data set and we can cast it to a latent space where it's just distributed all of that variance evenly, and you don't need to worry about cross-correlated variables or the inherent messiness of your data set. So neural networks are extremely powerful in that sense, that they give us this flexibility. You don't need to worry about those things that you used to worry about, those things that used to cost you so much time. I mean, I've read studies that show, on average, a data scientist spends 85% of their time just preparing the data and hand preparing features. Like, that's a fact of life. But with neural networks, this is no longer necessary. A lot of those problems that require you to hand prepare features just don't need to be done anymore. And even further, so another common problem that comes up when you're trying to clean data is if you have categories, like say you have country names, for example, and you haven't standardized the country name. Occasionally there might be a misspelled name, or it's commonly misspelled in another way. Or more accurately, you might have cases where you want to consider all countries in a certain region as being the same. Effectively, you're again applying your domain knowledge to the model, and you're saying, okay, well, United States and Canada, we want to bucket them together. So we might construct this feature from the data that allows us to bucket that together into our models, because again, we're applying that domain knowledge. Whereas with neural networks, and a fascinating thing you can do is you would have an embedding for that category. You let the model learn, and that embedding, which is essentially, it's just a vector that's learned specific to the model, is going to come out similarly if the model behaves similarly. So you can actually see, well, how this has actually an interesting side effect, which is that after you've trained your neural network and you've gotten these embeddings, you can actually look at them and you can say, oh wow, these two, USA and Canada, their vectors are very, very similar. The neural network has inferred in this case that USA and Canada, for the purpose of this model, are very similar, that they behave similar. So you get a lot of actually sort of side things that you can take out from the neural network that you never even tried before, that you would never get out of a classic model. So sort of the basis of my argument, I'm not saying that all doesn't improve results. Good data preparation will always improve results. It's simply that with deep learning, we have a new trade-off between your time as a data scientist and the accuracy of the model. And I kind of chart that here. So let's say you have, your boss says to you, this model, this thing that we're trying to predict is so important, so valuable, you can take a year to do it. Well, in that case, do as much data preparation as you want. Do as much feature preparation and hand coding and massaging of the data and cleaning as you want, because you've got that much time. But let's say your boss says to you, we need to get that model done next week, and we've got to move on to the next project. Like, get me the best result you possibly can in a very short amount of time. Well, you might actually be on this case where you're adopting deep learning can get you a better result in a much shorter amount of time than you could have with previous techniques. So that's sort of the basis of what we do. I create a free deep learning platform. Check us out, and I also provide AI services using our platform. So thank you. So next up is, oh wait, actually I guess I should, yeah, questions, of course, I always forget about that. Questions for anyone?
So I agree with the majority of what you said, and like deep learning is fantastic and all. Except that the kind of disagree with part that we have to accept that it's a black box, because like in Europe, there is this new privacy policy in terms of data that if you're making a business decision about the client, you have to be able to explain to them. For example, if you're denying a client a credit card, you have to say, you can't say that my deep learning network told me that you're not, so it must be explained.
So it is a matter of communication. So when you had a person evaluating that loan profile or making that business decision, the person is a black box. So that person may say, hey, I just had a gut feeling that this is a bad deal and I'm not going to go through with it. In many cases, that's a very acceptable business decision. So you're totally right, and the challenge there is getting people to accept the black box. There are new techniques coming out where we can dig into neural networks, but that's very time intensive. So I think it's just a matter of it's culture that right now we have these laws that are going to be very restrictive, that are going to force us to use one decision tree. I mean, even if you're using random forests, you're going to have a very hard time explaining it. So in those cases, maybe deep learning is not applicable yet, but I think the culture is going to shift, and I think we're going to accept black boxes from machines the same way we accepted black boxes from people, really. If you have a hiring manager and they make a hiring decision, you kind of just trust that they did a good job. So, any other questions?
Yeah, so it looks like this is a very universal tool for all problems. So, is there any ready tools available right now to?
Sorry.
I mean, looks like the deep learning.
Mm-hmm.
Technique is very universal to all the problems, right?
Mm-hmm.
So, is there any ready tool that we can use right now?
Yeah, absolutely. So, Electric Brain is one of those free tools. H2O, one of the other major companies doing a general purpose deep learning tools. TensorFlow, Torch, Microsoft has DPTK. But it depends a lot on your level of experience. My personal feeling on the subject is actually that the market for deep learning tools is not developed yet. That really there's only a couple of players, and there's an infinite number of business intelligence tools. I've actually found this. I was presenting at Big Data Toronto, and there's a cottage industry, in fact, of business intelligence tools. It seems like there's a continuous stream of companies that manage to get up to 20 to 30 employees, basically all doing the same thing, applying linear regression over big data sets or boosted tree over big data sets, and then presenting it on a dashboard. So I kind of venture and say that the tools aren't really well developed yet, but if you want to get into it, check us out, check out H2O, check out TensorFlow. TensorFlow is probably the most well documented right now, but that's it.
Can you talk a little bit about the actual implementation of what you've done? You mentioned GPUs, saw you're on GitHub. What is it implemented in? What libraries do you tend to call? What kind of interfaces do you support? How do you plug into, say, commercial software that's already written in other languages?
So underneath, there's several questions there. So underneath we use Torch. I find Torches to be it's sort of like the mainstay. It's not a whole lot of people have heard about it, but I bet all of you have heard of DeepMind, and that when they invented the network that could learn to play video games, they wrote that in Torch, and you can actually download the Torch code for that network. So Torch was sort of like the one that a lot of the advanced researchers were working with, but not a whole lot of people use it because it's based in Lua. People tend to like the Python-based networks. To your point, actually, I don't want to talk too much on sort of self, but why don't we chat after the show more about our software if you want to learn about that. Any other questions?
So it's an interesting question, right? You say you get pushback from the data scientist community.
Oh yeah.
Did you figure why?
Oh, absolutely, yeah. So I think there's a couple pieces to it. I like to feel like that maybe they're threatened by that deep learning might actually replace the necessity of having a data scientist. If 85% of what they do is data cleaning and data cleaning is no longer necessary, that would seem to imply that 85% of data scientists will no longer be necessary. But I just like to say that data scientists are just going to become 6 times more productive, and we're just going to get that much more usage of it. The same way when we make a more efficient light bulb, it doesn't mean that we use less electricity. Ultimately, what they've shown is that we just leave the lights on longer, and we do more of it. So I'm not totally sure. I think the main reasons are the ones that I went over. The fact that it's a black box model, and that they don't want to try to pitch that to their boss, and that they think it's way too CPU intensive, that it's overkill. Whereas what I'm bringing in part of our presentation is that I don't think it's overkill. I think it in fact can make them more productive. A server costs, even at the high end, $1 an hour. A data scientist costs much more than $1 an hour. So if you can use a server for an extra day, because it might take that extra day, but you've saved just 1 hour of data science time, I think it's worth it, and I think we can actually save 85% of data science time, even if it costs us, hundreds of servers in order to do it.
But I just add one thing. In my personal experience, the biggest problem with it is explaining the results to stakeholders.
Yeah, the black box, yeah.
They want business insight, and they want, like, when you're explaining a result to them, they need to understand it in their language. I can't say my network is spit this out. I have to be able to say because of this customer segmentation, etc. So in a language that they understand, and that's not possible with deep learning yet.
Yeah. All right. Should I hand off to you, Dragos? Jump in here with your heuristic question. Thank you, guys.